The night sky. People have studied it for millennia, seeking to unlock its secrets. We've come a long way in our understanding, and in the process, we've uncovered a surprising truth. Everything that we see, the stars, planets, life, makes up only about 5% of the stuff in the universe. Roughly 25% is what we call dark matter, holding galaxies together through gravity. The last 70% is known as dark energy, accelerating the expansion of the universe. Building on Einstein's theory of general relativity, scientists have ideas about how dark matter and dark energy affect the universe, and they can test their predictions without knowing the identities of these mysterious substances.
The way that structures form in our universe is very sensitive to the proportions of and characteristics of dark matter and dark energy. Without a certain amount of dark matter, there wouldn't have been enough mass in the early stages of the universe to form structures like galaxies that are very comfortable hosts that we live in. But without a specific percentage of dark energy, there might have been too much structure. So we need a very precise balance to be able to make the universe that we observe.
There seem to be some interesting tensions between observations that we've made of the early light in the universe, like the cosmic microwave background, and observations that we make of the local universe, so what's really near to us. We have a hint, however, that the local measurements give slightly different values. So the question is that real?
Now, new results from the Dark Energy Survey take us one step closer to figuring out how the universe got to be the way it is and what the future has in store.
The Dark Energy Survey is an international collaboration that aims at observing hundreds of millions of galaxies and taking pictures of them.
The primary science goal of the project is to study the distribution of galaxies in space, and that helps us better understand the expansion of the universe, and that's related to dark energy.
The multinational project led by Fermilab is based at the National Science Foundation's Blanco telescope at Cerro Tololo Inter-American Observatory in Chile. Over more than 300 nights, the survey charted about 1/8 of the whole sky, and includes the largest sample of galaxies ever used for cosmology, over 226 million of them.
The lens of the dark energy camera is more than 3 feet, and it can take pictures with a whopping 570 megapixels. This is far beyond the capabilities of our iPhone, which takes at most 12 megapixels.
One of the primary reasons we have our telescope in Chile is because they have these very tall mountains where the atmosphere is, relatively speaking, more stable. So the light, as it passes through the atmosphere, is going to be deflected less.
In the Dark Energy Survey, we use several probes, but the most powerful of them are galaxy clustering and weak gravitational lensing.
Galaxy clustering, it's sort of just is a name for the fact that galaxies, they aren't distributed sort of uniformly randomly in space. They exist in a web, and that's what we observe. We observe this web.
And more clustered galaxies allude to more dark matter in that region. So the galaxies serve to illuminate the dark matter scaffolding.
Weak gravitational lensing, it's a name for an effect that we can use to help understand dark matter and dark energy. I have a wine glass here, and the wine glass bends the light that passes through it. If I put like the base of this wine glass on the camera, you see that the image is going to be distorted. And importantly, that as I move the wine glass away, you see the amount of distortion changes, and that's exactly what we're studying with the Dark Energy Survey.
Figuring out those patterns is a complicated process. It's a bit like looking at an abstract painting and figuring out the order in which the layers were painted.
To do weak lensing and clustering, we need to understand how far away the galaxies are, so the distances from Earth to the galaxies. And we call this the redshift. So the higher redshift a galaxy has, the further away it is from us.
So redshift refers to the change in the color of light. So light has been shifted to be more red. When a galaxy is moving towards you, it would appear bluer for this reason, and when it's moving away from you, it appears redder. Redshift then is a measure of the velocity of an object relative to you.
In the Dark Energy Survey, we make photometric observations. So we observe each galaxy in different filters on our camera, and that allows us to pick up different features and measure the colors of these galaxies, which we use to determine their distances.
We need to measure how far these are with extreme precision, otherwise we can get biased results and then won't matter.
The Dark Energy Survey gives us a clearer picture of our universe than ever before. The results of our analysis are as impressive as the road to get there. We found that our measurements are well described by predictions that we make from the Standard Model of Cosmology. Measurements of the early universe are an exquisite fit to this model, but they probe the universe at an unrecognizable stage, when it's just a plasma of particles. Very different to the one that we observe with the Dark Energy Survey, which is teeming with galaxies and dark energy. So it's a beautiful test and a remarkable feat that one theory can describe billions of years of cosmic evolution. Now, our analysis best measures how clumpy the matter in the universe is. And it is intriguing that our measurements find slightly less clumpiness than what the early universe dictates. So although our standard model survives a more stringent test than ever before, there is enough ambiguity to keep us looking up. Now, the Dark Energy Survey has double the amount of data still to be analysed. So we're really just at the beginning of learning what we can from the darkness, and that's exciting.
The Dark Energy Survey has already done a lot of great science. Now, with the 3-year analysis completed, the best is still to come. The survey lasted 6 years in total. To unpack the full data set, the team will harness all the sophisticated methods that they've developed so far. In the process, they'll nail down the distribution of dark matter and dark energy with even greater precision.